Hey, what's up everyone? In this video, we are going to solve a question that is very frequently asked in coding interviews. Although we have solved this question earlier on this channel, today we will see another approach to solve the same problem, which is space efficient. By the end of this video, you will learn an interesting idea that is similar to the binary search and is very helpful because of its efficiency. Hey, Bhavesh here, and on this channel we learn and apply various data structures, algorithms to solve interesting programming questions. So if this is your first time on this channel, consider subscribing. Let's take a look at the problem statement. We are given an array of integers and a target. We want to find a pair of integers from the array that add up to the target. One thing to note here is that we are given an array that is already sorted in an ascending order. And we need to return the indices of two numbers that add up to the target, but this time the indices are not 0 based, instead they are 1 based. Let's see one example. Let's say the input array is 2, 7, 11 and 15 and the target is 18. Note that the array is in sorted ascending order and we need to return the pair of integers that add up to 18. In this case, we can clearly see that 7 and 11 add up to 18 and their indices are 2 and 3 because they are 1 based indexed now. So 2 is at index 1 and hence we need to return 2, 3 as the solution. Let's discuss what we already know about the problem from our previous video. So in the previous video, we looked at the brute force solution where for each number, we checked every other number and saw whether that pair adds up to the target. And hence, the time complexity of that solution was big O n square and it didn't need any extra space. From that point, we moved on to an optimized solution where we used a hash map and inserted all numbers at the beginning. Then, for each number, we found the other number whether that exists in the hash map or not. Because of this, the time complexity went down to big O n from big O n square, but space complexity increased from big O 1 to big O n. We also briefly discussed the third approach, that is using binary search. We found that search is a critical operation and hence we were trying to find ways where we can improve the search time from big O n, and big O log n using binary search was one of the solutions. The requirement is that array should be sorted and hence we can sort the array in big O n log n time, and for each number we can search the other number in big O log n time now. As there are n such numbers, the time complexity of the second step would be big O n log n and hence the overall solution is also big O n log n. The space complexity is constant time because we are not using any extra space. Today we are going to discuss the fourth approach, which should be ideally even better than the binary search. Note that in the previous solution, sorting of the array used to take big O n log n time. So even if we improve the second step, which takes big O n log n time, the overall solution is still going to be big O n log n because we are sorting the array. But in this problem that we are discussing, the input array is already sorted, so we don't have to do this step. Hence, if we are able to improve the second step, there is a chance that we can improve our time complexity even further. Maybe pause the video here to give yourself some time to think about it. Alright, the idea here is to capitalize on the fact that the array is already sorted. Let me ask you two questions. What is the minimum possible sum of two numbers from this array? Of course, it is first and second number because these are the two smallest numbers, so which is 9. Similarly, what is the maximum possible sum? This has to be 26 because 11 and 15 are the highest numbers. Now the target that we will receive has to be between 9 and 26. What if we add the first number and the last number? In this case, the sum of first and last number is 17 while the target is 18. To reach the target of 18, we will have to increase at least one of these two numbers But we already know that 15 is the maximum number in the array. So there is only one possible way of increasing the sum of two numbers, that is by moving from 2 to 7. Now we see that 7 and 15 add up to 22. 22 is greater than 18. So one of these two numbers has to reduce. But we have already checked that 2 plus 15 does not make 18. So we have to decrease 15 this time. And now we reach to 11. If we add 7 and 11, we see that we have reached the target, and hence at this time we can return the answer as 2, 3. In general, this is the idea behind this solution. We start at first and last number, and we increment or decrement the first number or this last number depending on how much is the current sum and what is the target. If the target is greater than what we can make at this time, then we increase the first number. When the current sum is greater than the target, we decrease the larger number. And this is how we at the end come to a solution. Now, some of you might be wondering why this solution always works. Although I cannot provide the formal proof of that, I can make an attempt to give some informal idea behind the correctness of the solution. Let's say the solution is a comma b, where a plus b add up to the target, and let's say a is smaller than b. In the previous example, 7 is our a. If you start walking from the right side, any number that you encounter when added with 7 will have sum greater than 18. Only when we reach at 11 that we find that 7 and 11 add up to 18. No other number on the right side is going to add up to 80. One possible doubt in the mind can be, what if we somehow miss this 7 and end up at 11 from the left side? Then there is no way to go back and we will never find the 7. But let me tell you that it is impossible to happen, because before reaching at 11, at some point we will be at 7. And as we discussed earlier, any number that is on the right side of 11 when added with 7 leads to the sum that is greater than the target. And whenever the sum is greater than the target, we keep the smaller number as is and try to decrease the larger number. So we will eventually end up at 11 from the right side before moving our left pointer any further. This is my attempt at giving you the informal proof of why this solution works. Let's take a look at the code now. So as discussed, we'll have two pointers, left, which will be at index 0 in the beginning, and let me take the size of the input, so numbers dot size, and our right pointer, int right, will be at the last index. Now until we reach the target sum, so while we haven't reached the target, so numbers of left plus numbers of right not equal to target. What we want to do is check whether this sum is greater or less than the target. So if nums of left plus right is less than the target, in that case, okay, so overall sum is less, so we have to increase one of the numbers somehow. So we will increase the left one, else we need to decrease the right, so right minus minus. And when we find that numbers of left and right add up to the target, we will come out of this while loop and return left comma right. Now note that left and right are 0 based indices and we want to return 1 based indices, so we'll simply add 1 to both of them. Let's run a couple of test cases. One is already provided. Let's add 2, 7, 11 and 15, and the target that we discussed 18. Let's see if our solution works. Well, for these cases, test cases, it works. We can now try to submit it. Well, perfect. So this solution works. Let's quickly discuss the time complexity one more time. So this is just an assignment and taking the size. Again an assignment, constant time, all of them, we go 1. Now checking this condition is a constant time operation. Checking this condition is again a constant time. This is also constant time. This is also a constant time. And at the end, last step is also a constant time. Now the question is how many times in worst case this while loop is going to run. In the worst case, we'll have to traverse the entire array. Either left pointer will go all the way to the right, or right pointer will go all the way to the left, or both these pointers can meet somewhere in the middle. At most, there will be n number of elements that we will look, and hence there will be at most n number of conditions that we will test. Hence, the overall time complexity of this while loop is going to be big O n, and this leads to the time complexity of our solution to be big O n as well. Now, as we are only using a couple of variables and no array in proportion of the input size, so the space complexity of this solution is big O1. I will post the link to the code with detailed comments and analysis in the description below. You will also find a Stack Overflow link which tries to provide the formal proof of why this solution works. I would really encourage you to check that link. In the next video, we will solve another problem that builds on top of the approaches that we saw in this video. I will post that video on Wednesday. Subscribe to the channel and hit the bell icon so you don't miss that notification. If you enjoyed learning something new today, give this video a thumbs up and share it. Post any questions in the comments below so either I or someone from the community can respond. I would also love to hear any suggestions and feedback that you may have. Don't forget to subscribe to Interview Recipes. See you next time and bye for now.